Hey everyone, how's it going? We're gonna start in just a minute. I see we have a few people already watching on the stream. Feel free to say hello to us here in the comments. Happy New Year. Naveed still awake?
Yeah,
Naveed is a champion because he's awake at what time is it? 8 o'clock?
8:15.
8:15?
Yeah,
When was the last
you,
time? When was the last time you woke up before the sun?
it was it was before the Christmas.
Oh, hey Emmy. Um, Emmy's my friend from London. Do you know her?
No,
She studied physics in London,
that's
and she
nice.
works a little bit with AI. So I was
A,
hoping she would join.
a perfect listener for the event then.
Cool. So yeah, let's get started while people are coming in. Um, I'm James, and really excited for today's session, which was proposed to me by Naveed, my friend, for what, a couple of years now, right?
Yeah,
And actually, we met because Naveed and I met when I was looking for a machine learning tutor a couple of years ago. And since then, he's taught me basically everything about neural networks. But today we're going to be doing something way more advanced, which is really cool because actually we both are a little bit engineers. Well, we both are actually engineers. I studied
yeah,
I studied aerospace and you studied electrical engineering, right?
yeah.
So we both have that, but then we also specialize in AI. So yeah, Naveed, I'll let you tell what we're going to be. Okay, we have already 9 people have hopped in. So hey everyone, thanks for joining. And if you just joined, just say hello in the chat and say where you're joining from. I'm in San Francisco, and Navi, where are you joining from?
Well, I'm joining from Melbourne.
From Melbourne.
Yeah,
So he's just gotten up early for all of you to do this special session. Hey, Nyan. Nyan is joining from the Netherlands.
wow, that's
Cool.
nice.
Great. So,
Yeah, I think we're gonna be covering all the continents.
yeah. Okay. I see Etna Library that's from Carolina. It looks suspiciously like my mom. So, great. We have 14 people. And if someone has a background in AI or physics, feel free to chime in and tell us what your research area is. And with that, I'll let you go ahead, Naveed, and introduce the topic for today.
Okay. Yeah, so the topic today is basically, as you people all know, the world is taken by this AI storm. You see neural networks everywhere, um, especially with the advent of LLMs. They are like now being integrated into every single field. But there's a intrinsic problem in the way neural networks or machine learning in general operate, which is they basically learn from data. And no matter what problem you are looking into, you need to have a huge amount of data set for that in order for it to work correctly. And even if you have the data, second problem is uh, these models suffer from a problem which is called out of distribution generalization. So, in simple words, what it means is if you have a data set and you train it on that data set, it would be working um, just fine on that data set or something that happens to be appearing similar to that. But if you then take that model and apply it in a different setting, it just simply doesn't work. A simple example would be you have, let's say, a tumor detection model. You train it on a set of data which comes from, let's say, a particular hospital where they're using specific equipment with its own technical details and stuff, like what's the resolution of the image, or what kind of camera is used, or something like that. If you train it on that, and you test its performance, it would be doing just fine. But if you didn't happen to take that model and apply it to a different hospital that are originating in a different setting where the equipment is different and other dynamics are different, in that case, it doesn't work. So this is called um, out of distribution generalization, and it happens not to work in those scenarios. And then there's this recent approach where um, the focus is, what if instead of just simply making the model learn from data, what if we try to incorporate some external knowledge into these models, which would make them able to, like, not just see what appears, but also have this inductive bias, which would tell it basically the underlying rules, or the basic principles. And if we happen to do that, it turns out that these models then not just only learn better, like they learn from much less amount of data, but also they generalize very well to different scenarios. So with that, the way the topic that we are doing today is called physics informed neural networks. So as you can see, it's in its name. It's what we are doing. We are taking physical laws and trying to incorporate those into the neural networks, and see how it affects or the learning of the neural network. Now, how we model physical phenomena? Well, we have what are called differential equations for that. So differential equations can be considered as the instruction manual of the universe. Basically, you can process all the major phenomena using differential equations. So if you want to model how fluid flows, for instance, how blood flows through our arteries and veins, we have the famous Navier-Stokes equations, which are very popular. You use them to model the fluid flow simulations and stuff. Or if you want to know how electromagnetic waves travel, you have Maxwell's equations for that. If you want to know how the dynamics of black holes, you have Einstein's equations. If you want to know the dynamics of atom to the subatomic level, you have Schrodinger's equations. So let me show you some examples of what is possible with these differential equations, and then we'll proceed from there. So this first video that I'm showing you is a simulation. Wait, do you see this screen, James?
Yep.
Okay, so here's a simulation of how the heart, which is this giant pump in our body, pumps the blood through our entire body. So on the left side, you see a side view where during diastole, the heart fills with blood, and as it shrinks, the blood is pushed through this major artery, which is called the aorta, and from there, it basically flows through the entire body. Now, this is a simulation. Of course, this is the top view. How do we model this thing, or how do we simulate this to an accurate level? Well, we basically solve the differential equations, the Navier-Stokes equation that I was talking about. Or if we then see this example, which is where two black holes merge together. So you have this bigger black hole represented by this giant black sphere, and then a smaller one. And these colors that you see are surrounding them are the ripples in the space-time fabric. So the the yellower regions represent stronger disturbance in the in the space-time fabric. And yeah, so you basically see when they become closer and closer, the ripples become stronger and stronger. Now, how do we? This is also a simulation. How do we do that? Again, we solve some differential equations in order to do this. Um, there's a third example. We see a bumblebee. Um, so here's a bumblebee, and when it flips its wings, it basically creates these swirls in the air surrounding it, and that's how it generates the lift and flies. And again, how do we model these fluids and these dynamics? We solve some differential equations. So yeah, so these are just like a bunch of examples which show you how powerful these equations are and how accurately they can model these different physical processes. Now, for the example today, we're not going to be doing something that hardcore because it's probably it would be taking a lot of time for us to do that. Would be doing a simpler example where we have what is called a damped oscillator. And for those of you who have studied physics, they probably would recognize this. Um, Basically, we have a mass attached to a spring, and if you exert a force on this mass, the mass starts oscillating, jumping up and down. And the problem here is, or what is it that we want to do is to predict the displacement of this mass with respect to time. So if I plug in a time, let's say what happens after 2 seconds, it would basically tell me where would be its mass after 2 seconds. So these oscillations that you see basically represent the displacement. So like at t, let's say at this point, the displacement is this much, and so on. Now, this problem, this phenomena is again modeled by a differential equation, and the differential equation that represents this looks something like this, where we have x double dot, which represents the acceleration, plus mu by m. Mu happens to be the coefficient of friction, and then we have this third term, which is So this is the differential equation representing that phenomena. And if we want to find out where would be this mass at a certain time t, we need to solve this differential equation. And if we happen to solve this differential equation, we would basically have our function where we can just simply plug in the time, and it would tell us where the mass is. By the way, I'm talking about differential equations again and again. For those of you who don't know what a differential equation is, it's just a simple equation, just like you have algebraic equations. But the difference is these equations involve a function and its derivative. So you see the function here is x, and its derivatives, x dot and x double dot. Yeah, so it involves itself and its derivatives. And that's what makes it a differential equation.
And the
And the
derivative,
solution, yep.
and derivative in the real world is something like speed or acceleration. How things speed up or change over time.
Yeah, so these equations basically model the changes that appear in any physical scenario. So the ones that I was talking about earlier, or this one, there's a change involved with respect to time. So if you want to model the change, you have differential equations for that. And just like I said, in order to solve this differential equation, you need to find this function which satisfies this equation. So if I happen to find a function and I take the double derivative of it and the single derivative of it and plug it in here, all of them should sum up to zero. And that's what we mean when we say the equation is solved.
Mm.
Now, there are certain phenomena for which you can solve this differential equation, what is called analytically, which means there is a perfect solution or a perfect function which you can figure out analytically working to some mathematical calculations. And at the end, you'll get a function which you can just simply plug it in and it would solve this equation. And for this problem, which is a simpler problem, fortunately, we do have an analytical solution. And the way we solve it, basically, this German mathematician called Leonhard Euler figured out that to problems like these, you have an exponential generic solution of the form this, where you plug it in, compute derivatives. I won't go through the mathematical derivation, but the point here is finally you get to a point where you have this perfect solution where you can simply just plug it inside the equation and it would appear to be satisfying this differential equation. Um, but that's not what we are doing for this problem. The goal here is um, to find solution to this differential equation using a neural network. Because, just like I said, for simpler problem like these, we do have a perfect solution. We can find them using analytical method. But for most general phenomena, like the ones that I was showing earlier, who are like complicated, difficult, highly complex phenomena, you don't have a perfect solution. For instance, how blood flows through our body. We don't have a function which we can just simply plug in and it would tell us how the blood flows through the body, or how, let's say, electromagnetic waves travel. So in scenarios like those, then we fall upon some other strategies to solve the differential equations. And one of the strategy is what is called numerical solution, where you just simply discretize the time and space and try to iteratively solve the equation. If you discretize the time, the derivatives just simply become differences, and then you can work out some mathematical tricks and tips, and then you can finally find the solution. But the problem with that solution is you only get the solution at certain points, which is called the mesh. So you generate these points, and you only get the solution at those specific points, and yeah, and that's how you solve it. Now, this is called a numerical solution, and the examples that I was showing you earlier are some of um, the results which are obtained with numerical solutions. And softwares like ANSYS or COMSOL, all of these basically imply a numerical solution to these problems. But the problem with numerical, and now I'm creating the case for why do we use neural networks instead of solving it through the numerical methods. Problem with numerical methods, first one, which I already stated, is that they require this mesh, and you have to iteratively compute the solution at every single point, in which is like computationally a lot heavier, and also you only get the solution at certain points and not throughout the spectrum of what that you're looking at. So for that reason, we need to, and we don't have an analytical solution because it's not possible. There's no function which you can just simply plug it and it would solve the differential equation. So neural networks happen to be like a solution right in the middle. It's not a perfect analytical solution, and it's also not a numerical solution where you just simply get the solution at certain points. It's approximating that function using a neural network, so you can call it somewhat an analytical solution. But it's not, again, it's not a perfect solution. But if we do it correctly, if you train the neural network correctly, it happens that the solution that you get is very accurate, and the computational resources required are far more less than what you would require with basically a standard numerical approach, which
Another
is
great example would be something like forecasting the weather, because forecasting the weather, it comes down to just a handful of very, very simple differential equations. But in reality, it's such a complex problem with so many elements that have to be forecasted, that it takes enormous supercomputers in order to do this.
exactly, yeah. So so let's go through the solution that is provided by a neural network. Well, before we do that, I just want to give credit to this guy who happens to be a lecturer at the Imperial College London. He has done a lot of work in physics informed neural networks. The resources that I'm using here, like this blog and the code later on Jens would be presenting. Um, so this guy needs credit for that. So yeah, so let's see how. Well, before I present what is a physics-informed neural network, I thought it would be better if I just briefly introduce what is a standard neural network for those of you who are not familiar with it. So a neural network, in simple words, can be considered as a universal function approximator. So if you happen to have some data points like x and y, a neural network, let's just draw it as a function f of um, x w is a function which we use in order to learn the mapping between an x and y. So for instance, a simpler example, suppose we have some data points 2, 4, 3, 9, 4, 16. You can clearly see that the input is x, the output is just the square of that number. So 2 squared is 4, 3 squared is 9, and so on. So because I deliberately put these points as a square function, you already know that the relation between them is a squaring function. But if we happen not to know that, a neural network can be used in order to learn that equation. So we can just simply use these bunch of data points in order to and train this neural network, and it would learn the mapping between this input and output. So the next time, if we then feed it a number, the neural network would know that the output is going to be a square of that number, and it can generate the output for us. Now, obviously, when you start with the neural network, you don't. It needs to be trained first on the data. It cannot know that in advance. And this W that you see here is, you can consider them as the knobs. So you just basically take this function and start tuning the knobs in order for it to learn what is the relation between this input and output. So if I'm feeding a 2, it should be producing a 4. If I'm feeding a 3, it should be producing a 9, and so on. And that's what is meant by training a neural network. So in training, we just simply tune these knobs in order for it to learn the input, how the input is mapped to the output. So that's like a generic overview of how it works. Technically, what happens is we have what is called a loss function. So the job of the loss function is to compute how different the answer of the neural network is from the true answer. So suppose the answer of a neural network, I call it y hat, and the true answer is y. So the loss function is doing nothing but just simply computing the difference between the the predicted answer, which is y hat, predicted by the neural network, and the true answer, which is just y. And initially, when these knobs are not tuned, the loss is going to be very high um, for obvious reason. And then as we start tuning these knobs, the loss is going to be varied. And the goal is to tune them in such a way which would reduce this loss function. And if we happen to like reduce this loss to a significant margin, this function, this neural network, would happen to have learned how to accurately produce this output from this input. So that's the job of a loss function. It is kind of a measure for us to determine how close we are to modeling this input and output. Now, again, obviously, we don't tune these knobs with our hands. There's a mathematical way of doing it. The technique is called gradient descent. Basically, the gradient descent algorithm just simply takes the previous weight and then it updates it by subtracting from it this term, which is the gradient of the loss function with respect to the weights. So the idea here is just simply you compute the gradients of the loss, which shows you how the loss is changing with respect to the change in the parameter. And then and this is the learning rate, which just kind of controls how much change you want to introduce. If this is bigger, the change would be bigger. If this is smaller, the change would be smaller. And that's how you update the weights. So this is in a nutshell how you update neural networks using this automatic um, algorithm called gradient descent, which requires computing these gradients. And as you will be seeing in the code, we will be computing these gradients to update these weights. Now, this is a standard neural network. That's how we do stuff. If we just simply want to have a standard neural network approach, how are we going to introduce the physics knowledge into it? And before we do that, um, let me remind you again that the problem with the standard neural network approach is if you happen to do that, um, the neural network would work for the distribution like this. But if you happen to go way beyond distribution, suppose I want to then compute what is going to be the answer to or the output for, let's say, 1000 or something like that, this still is not that much difference, but you kind of get the idea that if this is way different, then the output that is going to be generated by the neural network is going to be not so accurate. It would work very good for these points. So like if I have a new point, let's say 1, or let's say 3.5 or 1.5, it would be working accurately for those regions because it comes from the same distribution or the same region. If you go way beyond that, then it fails. And this is, so if you are doing this, it's called interpolation. So neural networks are good interpolators, but they are not very good extrapolators. So if you want to do this, where you go basically outside your distribution, then they fail. So this is the problem, and that's why we don't want to model that phenomena, the problem that we have, which is computing or finding out what is going to be the displacement of the mass with respect to time. We don't want to do that standalone with a neural network. We want to incorporate the differential equation that we have into into this neural network, which would basically embed this physics knowledge into it, and that's how it can solve it. So yeah, so the way we do it, it seems like we need to do something crazy, but the idea is very simple, but it is very powerful. So what we simply do is, with this standard loss, we just simply add another component, which we call the physics loss, and that's it. So if I happen to add to it this physics loss, and then train a neural network using that loss function, it would basically embed that physics knowledge into it. And what is going to be that physics loss? Well, the physics loss is just simply the differential equation that we have, which is so the physics loss is nothing but m double derivative of the function. Now I'll talk about what is u here, but dx squared plus mu du by dx plus ku equals to 0. Yeah, so this u is exactly the function that we are after. We want to find that function which would satisfy this differential equation. And in this case, we are trying to approximate that using a neural network. So this u is nothing but our neural network. And the goal is to find that by this training process, which should satisfy this. So if you just simply look at it, now the neural network not just only have to like reduce or minimize this term, but it also needs to minimize this term. Or in other words, if this solution, if this neural network happens to be perfectly solving the problem, this differential equation term should automatically sum up to 0. I shouldn't have written this 0 here. Yeah, so this is the term. And as we know that if it is a right solution, this term should automatically go to 0. So it's that simple. We just
Right.
simply plug in the physics loss here, and this is the physics loss, and it's just in form of the differential equation. You were saying something, Jan?
Yeah, because that green equation is just the equation for a spring because we know how springs work. And if you had a different type of system, then you would use a different differential equation to describe your system.
Exactly. Yep. So at this point, this is all that you need to do. You just simply take your standard neural network and add this additional loss term. Now, how do we do that? Of course, it's done in the coding. You'll see the details there, but just to kind of clarify what you're going to be seeing there is for the standard loss, we just simply take our normal data points, which we call x data, So the X data um, is the input, the standard input, and Y data is the standard output, which happens to be like we are just simply taking some of the points from that output that is going to be generated by the Spring, and we just simply take our neural network, provided the X data, it produces what is called Y dash or Y head data, which would be like the prediction of the neural network, and then we just simply compute the difference between these two using the standard loss. And for the physics loss, what we do is that we additionally sample the we just simply take some points in the time domain, which is like uniformly distributed points. We call them X physics, and the job of X physics is these are just some random, not random, they are uniformly distributed, but some time points, because this equation needs to be, if we want to incorporate this to our model, we need to be evaluating this at some particular points. We cannot just simply, obviously we cannot do it for like all the time. We need to pick some time points there, where we would compute this and then add those to the normal loss. So X physics, when you see that in the code, represents those time points which we will be taking and just incorporating, computing the differential equation and incorporating it to the normal loss by just simply adding to it.
Now,
And
in my code, I've actually already changed X physics because I found that it was a little bit confusing.
oh,
So,
okay, yeah,
so I've
yeah,
actually just called the variable in my own code
uh-huh,
sample times, which
yeah.
to me is something that for a first time beginner might maybe more
Okay,
obvious.
yeah. Well, yep. So I'll just give you a last example, and then James will take it away from there. So this physics laws, if you happen not to have understood what I was just saying, you can consider this physics laws as that additional information about the physics of the world, and this is just simply the empirical knowledge that you gain from the data. So an example which might clarify it to you is like that of a self-driving car. So, for instance, we want to teach to a self-driving car to avoid cliffs, because if you drive off the cliff, you just basically fall. If we wanted to do that using a normal neural network, we basically would need to like gather thousands and thousands of pictures of cliffs, and basically supervisedly teaching the self-driving car that if you drive off this cliff, you basically fall down. So you don't do that. And even if we do that, the self-driving car would learn to avoid the cliffs. But if you like change the scenario, suppose you those images all came from some normal area, like let's say yeah, cliffs are around a city somewhere. And then if you happen to drive that car, or if the car drives itself in some mountainous areas, the scenario is totally different. The distribution is now completely changed, and basically that car would fail to follow the not to drive itself off the cliff. So if we happen to like somehow teach this car that gravity is a thing in the real world, and if you drive off the cliff, basically gravity is going to pull you down, and you're going to fall. So that information, the law of gravitation, is like this physics laws. So if we happen to incorporate that knowledge to the training process of the car, with just a few examples, this car would now learn not to drive off the cliffs. And even if the scenario is different, when it sees Fourier, it's like it would know that there's a concept called gravity, and basically, if I go into the rear, gravity is going to pull me down. So it would avoid that. And with that, James, you can talk about the code.
Awesome. Thank you for so much for that perfectly clear explanation of how physics informed neural networks work because it's going to make my job so much easier, which is just exactly what Naveed has just described, but as Python code. So to make this fun, I will actually share this notebook with all of you. And I think some people here have probably used Jupyter notebooks before or Google Colab, right? So um, I'm going to share a link. I'm going to make this a public notebook. And anyone who wants to can actually just open this up and join along as we are coding or walking through the code for this really cool example. So yeah, just take it, open it up. Once you have it open, um, hit hit one in the chat just so I can know that we are ready to go along. Oh, and Z has just asked if there's good resource for intro to PINNs, and I think that the article that you
Yeah.
is perfect, right?
Yeah, so that blog article contains some cool blogs which explains these.
Cool. Um, yeah, maybe do we have that.
Um, yeah, so
Is it this one? Can open that up.
this is the code. So the blog is called benmosley.blog.
This one. Here, I'll throw
Yeah,
that in the
yeah.
chat to you guys. Cool. All right, great. So we have a couple people got the code as well. Gonna walk through this, and I have erased all of the results from the code. So we're going to be running the code as we go along, and actually we're going to be training the neural network. The first time we do it, we're going to be doing it the old-fashioned way, using regular neural network, which Naveed described really well. This is what a standard neural network looks like. It has an input, and then it has a bunch of layers, um, which are just a combination of equations, and then that all outputs into however many output values we have. In our case, we have one output value, which is the position of the spring, and the input, of course, is the time. So we're gonna first be doing this with the normal, traditional kind of neural network, and then we're going to be upgrading our neural network to actually understand something about physics. And what is it going to be understanding about physics? We're going to program it, or rather train it, by using um, the harmonic oscillator differential equation. Now, all that means is it's just something that's oscillating in space, like a spring or a ball on a string, or it could really be, or it could even be people turning the temperature up and down in a room using the thermostat. Like these are all kind of oscillating systems, which you can model with this differential equation. There was a
Yeah,
Yeah. Do you have
but yep. Barha has asked a question saying that if we have the differential equation incorporated into the like if we do have the equation isn't the problem
Mhm.
like already solved.
Yeah.
Yeah, so that's what I was saying in the beginning. The differential equation is it just tells you how change occurs, but to solve it you need that function which would satisfy that differential equation. So we need the function in order to satisfy that differential equation, because yeah, because that function is then used to compute the variable that we are after. In this case, we are after the displacement of the mass. So yeah, so like we have the differential equation, but we don't have the solution to it, which is what we are trying to do using a neural network to find the solution.
Exactly. So Burhan's question, isn't this just the answer that we're trying to get anyways? Can we just use this instead of training any model? And if you look at the way that this formula is set up, what we're trying to do is get the position as a function of time, right? But there's nowhere in here where we can substitute time and get the
Yeah,
position. Now, if you've done a basic differential equations class before, you will know there is a solution, which is this one, right?
yeah,
This is the exact solution. And if you have taken the course and you work your way through it, you'll get there. However, we're going to assume that we're just going to take this as an example because when you start using more difficult differential equations, it actually is impossible to get these, and that's where it becomes useful. So once you understand this code, you'll actually be able to do it for any differential equation. So that's the math. And as I mentioned, the first thing we're going to do is we're going to train a standard neural network. I will not be reading through every line of code. I'll be going through uh, one chunk at a time, fortunately for everyone here. Um, so I'll just run this first block, which is, let's see, I cannot connect to the TPU. Oh, it looks like I may have used up my
Oh,
CPU credits, but I could use a GPU instead, right?
yeah. I'm
So
wondering why you're using TPUs.
a GPU would be better. Is that right?
Yeah, yeah.
Okay. I
TPUs
assume
help. Yeah,
was
yeah. They help in certain algorithms. But generally, a GPU would be something that you would go with.
so you can change. So for everyone who's watching this, you can go to the runtime menu and you can click change runtime type. Now you'll probably be here
Yeah,
and you want to use a GPU.
yeah,
Um, Ideally, I don't know. I chose TPU. I thought that sounded cool, but Naveed's telling me that's not
yeah.
necessary. um,
And if you are rich, you can buy the subscription and use the 100 GPUs, which are like the powerful ones. But those are only required if you are doing something very heavy.
so the GPU is perfect for training a neural network.
Yeah,
So let me run this first cell. And this cell is just importing the PyTorch machine learning library, which is the foundational library that we're going to be using for this code, and then of course some plotting library as well. Now, all these functions do is they create images that we're going to be displaying later on. It's not relevant for the topic of today, but we need them for the display. And then likewise, this one is just a plot code, which will make the plot, which you'll see later. So now that we have all of that out of the way, we can actually show the code, which defines the architecture of a neural network. Now, as you remember, a neural network has an input layer, hidden layers, and output layers. And when all of them are connected to all the other ones, or all in one layer are connected to all the ones in the next layer, we call that fully connected. So here, in the architecture of the model, we define the initial layer, the hidden layers, and the output layer. And we even allow a variable here, so we could define the number of hidden layers that we want. So we could, in this case, it's three. In our case, I think we'll be using one or two, but we've made it flexible in that sense. And the activation function here is using this is tanh, so that's a tangent function, right? That's just the normal tangent function, right, from trigonometry.
tangent hyperbolic.
Oh, the hyper. Okay, so it's not
Yeah,
it's not exactly a normal one, but but it is an
a slight
approximation function,
yeah, a slight variation of the normal tangent function.
and it works great. And it's also you can also differentiate it as many times as you want to, which means that we can use it to solve differential equations.
Yeah,
It,
a
it can
slight.
it can be used to program the knowledge of differential equations into a neural network.
Yeah,
So we are going to be generating training data in order to train this neural network. Now, remember, we're still in the phase of we're just training a dumb neural network. Oh, actually, I skipped one thing here. Actually, so this is the speaking of the neural network. So this is the architecture of the neural network. The layers that we've described. We've described the activation function. Um, And we have some great videos on this as well, actually, that we've done that Naveed and I have done before. If you want to brush up on this, that you can find on my channel. But for today, we'll move on. And when we actually run the model, we actually run the neural network. This is the code that gets run, and it's just going through each layer, and then executing that layer one at a time. So we run the initial one, we run the hidden layers, and then we run the output layer and return the result. Almost forgot that part. So in order to train this, I'll just call it. It's almost like a dumb, unaware of physics neural network. We are going to use the real solution in order to generate data. Now, this is going to be. Did I run this one? I didn't run this one. I didn't run this one. Cool. So this is imagining we go out into the real world and we actually go measure a real system out there, and we're going to use that data. Like it could be astronomical data, it could be weather data, it could be
Yep.
heart data, and we're going to use that to train our regular, non-physics aware neural network. And we're going to see how that works. So
Yeah,
yeah,
because we don't have a real world data set for the spring, people talking on this spring to. So that's why we have the perfect solution already given to us by the analytical solution, and we are just sampling some points from it in
yeah.
order to use that as a training data.
So this is the data. Oh, let me run it. So I run this, and this is the data that we get. Now, Naveed, I actually added, just to make it more fun. I
Ah,
actually I
yeah,
actually added a bit of noise in there,
noise, exactly.
because it was
Yeah, that's a really clever thing to do because in real world you're not going to get these perfect sample points.
right.
Obviously, there would be some sensor errors when you are recording the points, so it's a good thing to have.
And I found it to be just a little bit too unbelievable when we're training a neural network and all of the points line up uh,
Yeah,
with the exact solution. So this is the exact solution, the blue one, and then these are orange points are the ones that we're going to train our neural network on,
yeah,
and we're going to find out if the neural network does a good job of approximating or predicting this blue line. Um, so that's all that this code here is doing, is it's just generating these dots and this blue line. So now we train a real neural network without the knowledge of physics. This is just a folder to store the um, this is just a folder to store the images that we generate, and this is the code to train our neural network on that data, that physics data from the real world. So this creates a new model with the architecture that we defined before. We have one input, which is time. We have one output, which is the distance that the spring or the object has moved. This is the dimension of how many of these green dots are in each hidden layer, and then this is the number of hidden layers. So we have three hidden layers, and we're going to use this for both. We're going to do the exact same architecture for both of the tests that we do. One with physics knowledge, one without physics knowledge. Um, Naveed briefly explained to you all what is backpropagation and how neural networks are trained. I won't go into the details because I cannot explain it as well as he can. But this is the algorithm where we specify the algorithm that does that.
yeah. So, so as like I was talking earlier, in order to make this neural network learn the mapping between the x and the y, the input and the output, we have these knobs in our neural network which we can tune, and that's how it basically learns the mapping. So the way we do it, I introduced algorithm gradient descent, And you saw in the gradient descent equation that we had these derivatives. So we take the derivative of the loss function with respect to the weights, and then basically we use those gradients to update the weights. So backpropagation happens to be a really clever algorithm for computing those gradients. Because if you just have a single normal linear regression algorithm, you can compute the gradients easily. But if you have a giant neural networks with hundreds and thousands of parameters stacked into these multiple layers, just like we have here, um, computing the gradients in themselves is a really painful job. And it was one of the reasons why neural network didn't take off initially, because neural networks has been existing since the 70s, or rather 60s, but there were just not clever ways of training them. If you make them bigger, first thing, there was not enough compute, and the second thing was that people just didn't know how to train these giant neural networks. And with the advent of backpropagation, which was like perfected by Geoffrey Hinton, we now know how to train them efficiently. So this backpropagation algorithm that you mentioned is just a way of computing these gradients which are used.
Thanks, Naveed. That's really, if you really need to understand one concept in machine learning, backpropagation is really the one to
Yeah,
learn and to understand. Um, because as he's mentioning, that's what makes this all effective, an effective technology. So we do that backpropagation 1,000 times, or however many times you want to do it in order to train. You'll notice that each time you do that backpropagation, your neural network, you're, as Naveed mentioned, you're fine tuning the knobs. Each time you fine tune the knobs, the neural network gets a little bit better, but normally the amount by which you can improve it diminishes, as you keep going. So we do that 1,000 times. Just pick that as seems like a good amount of time, and then we reset the weights, um,
uh, the gradients.
the
Yeah,
gradients. Okay, we reset the optimizer,
yeah,
uh, and we define here the loss function, which is defined as the mean squared error between the output of our model with the current set of weights that we have, and the data, the distance data, which is the points on the chart that I just showed. So the real world data that we're training on. So each time we take the difference between the real world data and the data as the model would predict it, we square that, and we're trying to minimize that as much as possible by fine tuning the model. And that's what a loss function does. And the rest of this is just plotting code to draw the results in a cool way as we're training it. So so let's do that. And when I did this earlier, it didn't take too long. Hopefully this shouldn't take too long either. Let's see, because it was okay. So here, so after 500, remember we're training in 1,000 steps. After 500 steps, we have something that looks like this, and then I think after 1,000 steps, we have something that looks like this. As you can see, it's learning very well where we have provided it with the points, and then it goes completely off the rail.
yeah,
Interesting. And it gets a little bit better here, but not a lot. And check
yeah,
this out. If we run this, actually, we even get an animation of how the model improves as we are running each back propagation step. So how
yeah.
how it is fine tuning over time.
That's pretty cool to see.
Yeah.
Yeah. So
So
this is what I was trying to elaborate earlier. That it's very good for interpolating stuff. Interpolation means estimating what happens between those points. This is where the data is coming from.
yeah.
So in that distribution, it's perfect. But as soon as you go outside the distribution where you don't have any training points, yeah, it just doesn't know what to do. So this is what all the neural networks suffer from, no matter if it's computer vision or natural language processing or anything, even your LLMs. If you try to ask it something which it has not seen before, it's not like it's memorizing whatever you have thrown at it. It can interpolate, it can find points in between, which is not in the training set. It's just that it's the same distribution, same type of data. And if the data type is different, comes from a different distribution, it fails.
And this is like a real problem, because imagine, okay, if you're measuring something on a spring, you can wait and watch it. But if you're out in the world, maybe measuring a real world system,
Yeah,
and you want to predict what's going to happen, that this time might actually be in the future. Um,
exactly.
so you cannot actually get all of the training data that you want, and
Yeah,
then you're left with, okay, what physics knowledge do I have that I can add to this?
yep,
So whether it's an oscillating system, maybe it's in the case of the weather, the example I used before, you don't know what's in the future, and you might not even have all geographic areas. So you're
yeah,
gonna have missing data,
yeah,
and that's what we're gonna fill in with the physics informed neural network.
yep.
So as Naveed mentioned before, if you all were paying attention, um, all we have to do in order to update the model is to add a physics loss to the model loss. So the physics loss is based off of the unsolved version of the differential equation. So it's based off of this equation here, not this one, because if we had this one, then it would be all the problem would be solved. But it's this one here,
Yeah,
and we don't we're not entirely using that equation. We're combining it with the results of basically um, a standard um, neural network training.
yeah,
So the code here is actually exactly the same. It's a lot of code here, but it's exactly the same as the one we just showed you, except for two places. One is these two lines of code up here, where I have new, and then the other is this chunk of code here. The rest of this, okay, this has been increased from 10,000, from 1,000, or to
yeah.
10,000.
That's a lot of increase, yeah. But it doesn't mean that because you have increased the number of training iterations, that's why it's learning better. Even
No,
if you would have trained the earlier neural network for 20,000, it wouldn't have gotten it. It's just that the earlier neural network, the losses decrease so quickly that
yeah.
there's no point in training it further. That's why those iterations are lesser than these ones.
We'll have a look here. Even after 1,000 training steps, we can tell it's not going
Yeah,
to be better.
yeah.
It's never going to. It's still
Replicate,
getting a
yeah.
little better, but it's never going to fit this curve, right?
Yeah, it's not following the oscillations. It's just that yeah, that the line is kind of becoming more and more
Yeah.
towards the center.
So what is it that we are actually adding? So this long line of code, it kind of confused me at the beginning because it's rather long for what it does. All that it's doing is it is choosing a set of points, which go not just in this area where we already have data, but it's choosing a set of points along the whole x-axis here, um, across the whole domain of the entire problem we want to solve.
Yeah,
Now we don't have the answers, we don't have the output. It's not like
yeah,
we're training, but we're just choosing a set of input points that we want the model to be able
exactly.
to answer.
Yeah, so that's the key here. We are just sampling the time, not the answer. Because if we would sample the answer, then there's we just basically, yeah, it defeats the argument that we are doing physics in formal neural networks, because a normal neural network would have done better if you would have sampled throughout the time.
So the way you can think about it is that we're choosing the times at which we want to use physics in order to
Exactly. Yeah.
improve the training.
Yeah.
And
And
that
PyTorch,
physics,
yeah, PyTorch has this weird way of like doing stuff. All this is just a bunch of points, but yeah, you have to set the required gradients to be true, because these are the points we are going to compute the gradients um, for. That's why like PyTorch wouldn't be able to compute the gradients if you don't set them these gradients to be true. So it's not something that is like machine learning required itself. It's just that the way PyTorch does stuff.
that is honestly really rather confusing kind of syntax.
Yeah,
So I would not worry too
that's
much.
why I prefer TensorFlow.
Okay, but don't worry about this here. Really,
Yeah,
it's not illustrating the concept that we need to teach. Now, the real important part here is, as Navi was explaining in the theory part, is that we are creating a loss here. If you look where I'm selecting here, we're creating a loss by adding together the regular loss, which is the mean squared error. This is the same thing that we just had, and a new physics loss. Okay, and we can combine these in any sort of amount. We can add a little bit of some, a lot of another, a lot of one, a little bit of another. So that's experimental, how much of each loss you use. But adding them both together is the critical part. And the way that we do that is we take. I'm going to go back up to this equation one more time. Um, we we calculate these derivatives based on the neural network model that we currently have. We substitute those in, and if the model is perfect, according to the physics, then this equation will be true. You'll have zero on the left side and zero on the right side. Now, that's not actually true. There will be a small difference. And that's the difference that we're going to use as the physics loss function.
exactly. Yeah,
So just to reiterate, these values, the the second derivative of x with respect to time, the first derivative of x with respect to time, and x are taken from the model itself, and that's
yeah,
that's sort of the trick of this whole thing. That's the
yeah,
magic trick of the whole thing.
yeah. Just a quick comment on the mass and the coefficient of friction. These are just some values that we put. For every problem, there will be different, because you would have a different mass. It could be a bigger, smaller. I mean, it varies. We are just doing it for a specific example scenario, but that doesn't change the concept that we are demonstrating. So yeah, so we just assume some mass value, some coefficient of friction, and some spring constant, and the combination that we choose makes it a particular type of oscillator, which is called the damped oscillator, or
Mhm.
the underdamped case, where the oscillations dampens over time. So there are different scenarios where you might not see the oscillations. You can just quickly yeah, drop down and come at the origin. But for this case, the spring does oscillate. So that's the case scenario we're looking at.
Right. So that's the assumption that we're using to train this model. And this model will only understand the physics of that particular system. But you could train it on any physics using the differential equations that you have available.
Exactly.
So these long, rather confusing looking functions, and I have to admit, this is the part of the code that really threw me off the most. Um,
Yeah.
Basically, I've kind of written it out here. So in that equation that I showed above, this is what we're substituting in for x This is what we're substituting for dx dt, and this is what we're substituting for dx squared dt. And
Yeah.
what this is saying is it's saying PyTorch, have a look at my model that I'm training, that's halfway trained right now. Um, Figure out for the for the given um, for the given set of sample points that I've chosen, which are times for the given set of sample times that I've chosen that I want to be able to predict for. What what are these derivatives going to be based on the model that we have, and then plug that into this, which is the actual equation that we just looked at, and then figure out what's the difference between where it should be. Then that's the loss, and then that's the loss that we multiply by some constant of our choosing, and then we add to the first loss.
Yep. So these two lines of code are just simply computing the derivative and the double derivative that are used in the differential equation.
Okay, let's do it. So I guess this should take a little bit longer, but we do have we are able to see the training of the model as it's coming along. So as soon as it gets to here, it says 6,000 steps. So as soon as we have trained the first 6,000 steps, then we'll get a chart. Does anyone want to take a guess at what we are going to see once we get there? So we already have some results already. Okay, well, let's look at the last results we had. They look like this. Okay, does anyone want to take a guess at what we're going to see? Let's have a look. Okay, interesting. So as you saw before, we are training on this real world data here, these orange points, and then the physics loss is being calculated at all of these green points. So this is where it's being updated or informed with the differential equation that we chose. And we can already see now that it's
Yeah,
behaving
just
way more close to what we'd like it to
way
be.
more better. Yep. Just in the first 6,000 iterations,
Yeah,
it's literally following the real solution perfectly.
here it's almost spot on.
Look at that.
Here, perhaps this is due to a bit of noise. It might be a little.
Yeah, yeah. So if you would have seen this earlier, this is sitting exactly on the top of the original solution, but because of that noise, it's kind of throwing it slightly off.
That's cool.
Yeah, amazing. See how quickly it just jumps to those oscillating points.
And that's it for the code.
Amazing.
Go ahead and run this for yourself. You all have access to the code, so you can actually just run this in your browser. You don't need to download anything.
Yeah.
Any questions? We've been here for an hour, so we'll definitely wrap it up. But we'll stay on for a few more minutes, um, just to see if anyone has some questions.
Oh, so the question is there an algorithm that tells you the optimum number of training steps for each physics problem, like this harmonic oscillator? Well, there's not a specific algorithm which would um, give you a number that these are the number of iterations you need to train. This is something that, yeah, so that you can see for yourself. There are multiple ways you can stop the training of the model, like based on multiple criteria. One of it is, which is often called early stopping. So you can set a number of training iterations, say 1,000 or 20,000, but then you can put an early stopping condition saying that if the decrease in the loss is below this threshold, then just stop training, because we are just wasting our compute resources, and there's not significant reduction in the loss. So that's at that point just stop training because that's enough. So it's one way of doing or of figuring out how many optimum number of iterations are required. But again, there's not a specific formula which would just like tell you that for this particular physics problem you need these many iterations.
Yep.
You're welcome. Yeah. So um, so this is what I'm doing for my research. The problem with solving these problems using numerical methods is sometimes the computations grow so much that takes weeks to figure out just a simple or to simulate just a small part of a particular area. So I was looking at these simulations done for the aorta, which is the major artery in a human body. And they were creating this 3D model to find out how the blood flows there. It was just a small part of the artery, not um, the full artery, let alone the full circulatory system. And yeah, and it took lots and lots of compute resources just to do it for that part. And then I saw this another some researchers, I forgot where they were, but they tried to replicate the results using um, physics informed neural networks, or yeah, the neural networks. And like the reduction in the time was enormous. It was not just like two folds or three folds, it was thousands of folds reduction in the compute time. And once you have this algorithm trained, you basically get a sort of analytical solution where you just plug in the time, you get the answer. If you would have done that through a numerical method, you would need to like compute all the previous points, the mesh, in order to predict what's going to happen in the next time. But with an analytical solution, you can compute the result at any instant of time instantly without relying upon any previous knowledge.
Okay, Naveed, I have a question.
Mhm.
Um, if Now there's a lot of solutions out there on the market for finite element analysis kind of things.
Yeah.
So making real world simulation of physics. How many of these software programs are already integrating AI, like neural networks, kind of this kind of style thing that we're doing today?
Oh, well, yeah. I mean, what I did for my master's research, where I used Ansys Maxwell for simulating an electrical transformer, um, I was like working with the 2021 or 2022 version of it. Um, yeah, and I didn't see anything that would have like incorporated any machine learning. So
Right.
there are standalone approaches, standalone Python libraries which are trying to do it, but in these established softwares, things like COMSOL or
Yeah.
Ansys Maxwell, till 2022, I didn't see anyone incorporating those. Maybe they've done it now. Right now, I'm not looking into those softwares. I'm rather doing it using MATLAB, which is what because of my supervisor's done that in MATLAB. So yeah, but I think maybe they are now looking into it because of the enormous efficiency of neural networks as compared to a traditional software.
Yeah.
Yeah.
Great. Cool. Well, thanks everyone. If there aren't any more questions, then we'll end for now. But feel free um, to hit us up on LinkedIn or elsewhere, and I will drop all of the important links that we showed you today in the description of this video.
Yep. Thank you everyone for joining.
Thanks, everyone. If you have something that you want us to cover in the future, just let us know.
Yep.
All right.